All right, welcome to today's physics lesson. We're going to be beginning our one-dimensional motion, and we're going to start here with the concepts of position, displacement, and distance. So, as is usually the case, I'll start the lesson by giving you a list of your learning targets. These are the things that, by the time the video is over, that you should understand or be able to do. All right, so obviously you should understand the three terms. You should be able to calculate these three values, position, displacement, and distance. If you're given a written, pictorial, or graphical description of the object's motion. And then finally, you should understand the significance of either positive or negative position and or displacement. All right, so here we go. So this chapter is, as I said at the beginning here, called one-dimensional motion, which means basically that all of our motion will take place along one straight line, okay? And because of that, it's usually going to be helpful to visualize the motion on a number line, okay? So position represents an object's location on that number line. All right, so maybe our little world is down here. Maybe this number line here. Maybe these are, I don't know, let's say these are kilometers. All right, and maybe since we're talking kilometers, maybe this takes place in Canada. So here is the Canadian capital. All right, and then maybe 4 kilometers down the road, there's a Tim Hortons, which is Canadian. And maybe 6 miles, or kilometers, sorry, the other way we've got a, what else is Canadian? Alanis Morissette. All right, so here's Alanis Morissette's house. All right, so when we talk about position, we're just talking about the location, all right? So in this example, we would say the position of Tim Hortons is 4 kilometers. And the position of Alanis Morissette's house is -6 kilometers. All right? So position is simply the location of the object on a number line. All right? A couple things that I want you to be aware of here. Let me erase this here so that we've got a little room to work with. All right, so a couple things I want you to be aware of. So first of all, in order for this number line to have any significance at all, in order for position to be meaningful, we have to agree on the location of our origin. All right, so in this example that I just finished, our origin here, where 0 was the Capitol building, right? Okay. All right, next thing you should be aware of is that, as I alluded to here, an object can have a negative position, but that only works if we agree which direction is negative, all right? Usually in this class, we're going to use the same sign conventions you use in math class. So specifically, if you're talking about a number line that runs right and left, right will be positive, left will be negative, and if you're talking about it up and down, then up will be positive, and down will be negative, all right? And then finally, position does have units, and I began this example with that, right? I said, all right, we're in Canada, so we're going to deal with kilometers, all right? But the big thing to notice there is because we're talking about position, those units are going to be units of distance, okay? Now, over here on the side, I drew another number line, right? So maybe this is, maybe it's a cliff, right? So here's my cliff, and here's my dude. And then here's a ball, right? And so let's suppose that somebody kicks the ball up into the air, and it does this, right? So the idea is the starting position of the ball looks like it was, I don't know, close enough to 0, right? And then it goes up to a position of 8, and then goes down to a position of -10, or whatever. Okay? So there you go. That is position. All right, now displacement is definitely related to the idea of position. Oops, sorry. So our definition of displacement is an object's change in position, okay? So, wow, these things are not working here. There we go. All right, so basically all that displacement does is it tells us how far an object ended up from its starting point, okay? And when I say starting point, that just means, you know, some point in time, okay? So the displacement tells us how far the object is at some later point from where it was at some earlier point. This will make a lot more sense once we do an example here, all right? Next thing, displacement, much like position, can be either positive or negative. All right, and if we know the starting position and the ending position, then displacement, notice the symbol for displacement. The symbol for displacement is delta x. So hopefully from chemistry you know that delta means change in, x means position, right? Okay, so so going back to our Canada example from a minute ago, we had the capital here, right? We had Tim Hortons over here was at a position of 4 kilometers, and we had Alanis Morissette's house over here, right? All right, so let's suppose that Alanis Morissette drives from her house, so here she is. There's Alanis Morissette, and she's going to drive from her house to Tim Hortons and then back to the Capitol. She's got to talk to the Prime Minister. Okay, so in this example, you know, the distance she drives is far. For displacement, though, all we care about is how far she ended up from her starting point. So she began here. So her initial position in this example was -6 kilometers. Her final position, in here I means initial, F means final. So the final position in this example is 0 because she ended up at the capital. And as a result, her displacement is, well, I mean, you could literally just count, right? So you'd say, well, 1, 2, 3, 4, 5, 6 kilometers. Or you can do the math, right? Final position minus initial position. So her final position was 0. Her initial position was -6. 0 minus -6 gives you 6 kilometers. Now notice that positive answer there, the fact that we got positive 6 kilometers, has meaning. It means that she ended up 6 kilometers to the right of her beginning position. Okay? All right, let's flip that around. Let's suppose instead of this, what if we had this? Oh no, I didn't mean to erase all of my landmarks. All right, so here's Tim Hortons again. Here's Alanis Morissette's. Man, why can't I think of any Canadians? This is the Prime Minister's summer cabin. All right, so Tim Horton leaves his bagel store, and he drives to the Prime Minister's house to deliver some bagels, and then he goes back to Alanis Morissette's because she forgot her receipt. All right, so in this example, my initial position is 4, and my final position is -6, right? These are all in kilometers. So in this example, Tim Hortons' displacement, the person Tim clearly is the owner of Tim Hortons, his displacement is going to be final position minus initial position. So his final position was -6 kilometers. His initial position was 4 kilometers. When you subtract, you get -10 kilometers, which just means that he went backwards, or I guess for us, left 10 kilometers. Now, that doesn't mean he was going left the whole time, right? Some of the time he was going right. Okay, but overall his displacement is -10 kilometers, or 10 kilometers to the left. All right, so displacement includes the direction. All right, so so notice, as I said, that when we're discussing displacement, we don't care about the path the object followed. All we care about is where did we start and where did we end. And I think that those last 2 examples illustrated that. All right, now, inherent in the idea of displacement is the idea of time. This is, hands down, the thing that people struggle with the most in this first chapter. So I'm going to try to start stressing it now when it's not that important, and it will become more important. All right? So the idea is physics is about motion, right? We're going to have things that move through space, and motion takes time, right? It takes you time to get from one place to another, always. So it is super important that you identify what time interval you're looking at, okay? So just be cognizant of that, all right? And then more often than not, a problem will just simply give you the displacement, right? Like it'll say, Roy drives his car 300 miles. And then you just know, well, that's my displacement. If the problem doesn't say anything about direction, then just assume that the object is moving in a positive direction, okay? So in this example, Roy drives his car 300 miles. It doesn't say what direction it is, so let's just call the direction forward, which we will assume to be positive, okay? All right, now distance is very similar to displacement, but is not the same thing. All right, distance is the total length of the path that an object follows. All right, it is always positive. You can't go a negative distance, as Ferris Bueller found out trying to take the miles off the Ferrari. Sorry, old reference. You probably don't get that. Now, when discussing distance, you have to care about the path that the object followed, right? So like in that last example, we had Tim Horton, right? He went from here to the Prime Minister's house and then back to Alanis Morissette's house, right? So here, the distance, I don't know if you remember, but the displacement we just found a minute ago was negative 10 kilometers, right? But the distance would be much farther than that, right? The distance would be, well, let's see, 4 miles to get to 0, 10 miles to get back to whatever was over there, the Prime Minister's house. So we went 4 miles plus another 10 miles, and then another, what, from negative 10 to negative 6 would be another 4 miles. So the distance here is actually 18 miles, right? Because that's how far Tim Horton had to travel to get from the restaurant to the Prime Minister's house and then back to Alanis Morissette's. All right? So, sorry, I don't know why I think this Alanis Morissette thing is so funny. I will continue to laugh at my own jokes, even though I'm teaching in an empty classroom. All right, so that's the deal with distance. It's the total length of the path an object follows. Distance is always positive. We care about the path. We almost never use distance in physics, which is why I kind of plowed through that last example. It almost never matters. Pretty much we're going to really just focus on displacement, okay? It is worth noting, though, that if the object moves in a straight line, then the distance equals the magnitude of the displacement. In other words, if you drive 10 miles straight north, then both your distance and your displacement are going to be 10 miles. If you drive 10 miles straight south, then your displacement's negative 10 miles, and your distance is positive 10 miles. Okay, so that's what the word magnitude here means. The word magnitude basically just means the size of the value. Okay, which brings us to this next idea. In this class, we're going to deal with two different types of numbers. All right, so let me just show you what the two are. So a vector is a number that has both magnitude and direction. Okay, so examples are displacement, right? So you can say your displacement is whatever, 10 miles south. Or for us, since we're doing one-dimensional motion, you could just say negative 10 miles, right? But the idea is that negative sign, or the word south, indicates direction, right? Now, a scalar is a number that does not include direction. So distance is an example of a scalar. Ferris Bueller cannot drive that Ferrari negative 10 miles, even though he needs to take the miles off. The only thing that he could do is add 10 miles to it, all right? So if direction is important in the value, it is a vector. If direction is not important, it is a scalar. All right, we will be talking in a fair amount of detail about vectors next unit, okay? All right, now, in this class, we're going to be studying motion. So as time goes on, the object's position is going to be changing. All right, now, an easy way to describe an object's motion is with what's called a position time graph. All right, when I see you in class next, we're going to do an activity that will hopefully help you better understand what a position time graph is and kind of how they work, okay? And it says here, here's the basic idea. Yeah, I guess we can talk about that. All right, so in that example that we just did a little bit ago, we had, who was it? Tim Horton, right? Started here at 4, and then he traveled all the way back to a position of negative 10, and then forwards to 6, right? So we could make a position time graph, right? And what that would do is we'd have two axes. The horizontal axis will always be time, and our vertical axis here is going to be position. Okay, and so let's mark these off. So 0, 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. I need to put units on here. They were kilometers. Negative 2, 4, 6, 8, 10. Negative 2, negative 4, negative 6, negative 8, negative 10. All right, and so in this particular example, the our dude started at a position of 4. Okay, and you know, maybe he was hanging out there. Maybe he was at the store making bagels for a little while. Okay, then at some time, he began moving in a negative direction, right? And he moved to the left until he got to a position in -10. So at some point later on, so this is him moving to the left, right? So at some point later on, his position was -10. So I don't know, whatever. Maybe it looked like that, right? And that's showing you that his position went from +4 down to -10, right? Okay, and then after that, he turned around and he went back to the right until he got to a position of 6, right? So, all right, so something like that. Now, the fact that there aren't numbers here makes this complicated, but the main thing I want you to see is that when you draw, I don't want to say this, when you draw this mess, it's cool because it shows you everywhere that, in this case, Tim Horton traveled to, right? But it doesn't show you when he got there, all right? Now, this position time graph allows us to do the same thing. It's us the same information, right? That he started at a position of 4, he went to -10, and then forwards to 6, right? But it also gives us some information about time, okay? And so, you know, if there are numbers on this, I could figure out, for example, when he passed to the Capitol at a position of 0, or, you know, what time it was when he got to Alanis Morissette's house, or whatever, all right? So anyway, that's going to be kind of the point of the lab tomorrow, the activity that we do in class tomorrow, all right? So I think we will stop there. There you go.